Okay, good morning, and many thanks to organizers for being here. So when you speak about computation and modern computation, the process of looking for analytic solutions of different representations of the transient behavior of Markov processes first, and actually of the solution to any system of differential equations, linear differential equations, possibly infinite. So I will do a very short introduction and then the outline of the rest of the paper of the presentation and the contributions I will describe. Let me first start with this idea of Sigmund building a new meaning of the word duality and probability. Here, what he did was to propose a transformation of a Markov U1, having some specific properties I will describe later. The only point of this slide is to underline I live in a discrete world, like we all, according to physics. So my chains are in discrete spaces, not continuous ones. And the transformation of the process of the chain translating to the transformation of the matrix, the transition probability matrix, if you are in discrete time, or the rate matrix in continuous time. And the difference in notation is because there are some difference in the matrices, even if we are speaking about the same probabilistic transformation. The Sigmund dual exists only if the original chain has a monotonicity property, I put here, but basically it's saying that think of a birth-test process going from left to right. If you start there, the probability time t to be to the right of this point is less than if you start here, closer to the barrier, or if you start here. So this duality idea works only under this condition. The other thing is not very visible here, but this order here on the states means that the way you name the states has an impact on the property. And that means, I will show you the examples. If you take a birth-death process, you will have this property immediately, even if it's hard to prove. But of course, if, like any normal human, you name the states 0, 1, 2, 3, 4, 5 going to the right. But if you are ill in some way, you put 0, 1, 2, 3, 4, then you are losing the property, and there is no dual. So what's the point? The point is that in some cases, so far, always in some kind of fundamental model, having a name in the literature existing, this idea leads to a better representation, sometimes much better representation of the target, of the transient distribution of the chain, the model you have. For instance, for fundamental Qs like those ones. This is long to explain this. The literature is rich today on that. So that's my topic, transient distribution of a Markov chain, and more generally of a linear system of differential equations. The idea is start from this probabilistic concept of duality. We started with Qs, and we applied that to Qs, of course, for performance evaluation, to other Markovian models for reliability, rare event analysis, etc. And we discovered in the way, more recently, that actually the nature of this, the properties we are using are algebraic in nature. You can prove everything without referring to the probabilistic underlying model, and that means that everything I will say is valid for any arbitrary matrix. So in the introduction, I will do a short zoom on the MM1, the most famous Q. So these are the differential equations, Kolmogorov equations. The unknown is the probability of having J customers in the Q at time T. So the state space is 0 is the integers, the positive integers. You go to the right with lambda, and you go to the left with mu. The solution, the first closed form solution to this system of differential equations is this one, where these i's here are Bessel functions. It was done in the 50s, and the idea the initial idea was always to move to the generating function. In space, you go to your variable z in my notation, and in time, Laplace, so generating function for space, Laplace for time. So you get a rational expression, very simply, of the double transform, but there is an unknown function inside the Laplace transform of the distribution at state 0. And I don't remember who first, I don't know if it is known, make the observation that the poles, the potential poles of these double transforms are explicitly known, and you can prove easily, you can check that one of them is inside the unit disk, the other one is outside. But the function in Z is analytic, so this pole must be a root also of the numerator, and then that's the extra equations allowing you to obtain this unknown parameter. And inverting, you get the expression in terms of Bessel functions. There are, this comment is relevant, it's not good at all for numerical exploitation. It has bad numerical properties. There are other, after this one, other representations have been published, integral, most of them, and none of them is good except one using tricks, trigonometric functions, that is okay for numerical analysis. Then we go to our contribution a long time ago with other people at Inria in France. And this is our solution, this Poissonian series, where this coefficient here is explicitly known, this thing. This comes from uniformization, if you are aware of that, a very simple way to move a problem in continuous time to a problem in discrete time, to move differential equations to difference equations. Using that for free, you get these properties. Numerical stability, the thing you are writing is always stable. And you can control a priori the error because you have this series here. You will have to trunk it. And you can decide before starting in time 0 how many terms you need to get an error less than 10 to the minus 5. And moreover, what you are doing as a probabilistic interpretation, and that led to many extensions, applications in many other problems. I will not enter basically the path to obtain that. Move it to the generating function of the matrix P. And P is the uniformization matrix, identity plus rate matrix of the MM1 divided by something larger than any rate in the process. And then you can invert. The key thing was a theorem describing the structure of this generating function as a float form with factors depending on different parameters. And that was the way. And then once you have these coefficients for P coming from the matrix generating function, you can invert. You can put them here once you have it explicitly, and that's the expression I showed. Just a comment, a very recent comment on this old topic. A key part of the process was to make appear in the development Catalan numbers. They appear naturally in the inversion last slide. The last slide. These are the Catalan numbers. They disappear then in the different computations to arrive at the form I showed in the here. We don't see anymore the Catalan numbers, but in the process, they are the key. I mean, a key element in the development. We didn't know exactly why they appear, but it's this year, this a paper in American Mathematical Monthly showing somehow continuing the work by Évariste Galois, or showing that the discussions among the root of polynomials was not close as we all tend to think with the work of Galois. In particular, they show that for any polynomial, they can provide an expression of the roots, the real roots. And the key is an extension of Catalan numbers and must be a connection with what I showed before. So, as I said very briefly at the beginning, when you apply this, there are many strange things that happen. For instance, the order of the states, the names of the states matters, and somehow the chain is the same. In some cases, you have, when the space is infinite, defective duals, which are hard to manipulate. And you have conditions on the parameters. For instance, imagine here, it doesn't happen for the MM1, but something like if lambda is less than mu divided by 2, there is a dual, and suddenly for lambda equal to mu divided by 2, there is no more dual, and you cannot do what you have done before. That looks strange. So we explored the idea of keeping the same formally, the same transformation, but forgetting about Markov chains, and everything works. And we observed that one of the important things to observe is that you need two transformations, two dualities now, which we call it power dual and exponential dual. And what I will do in the rest is I will describe this one, the shorter. I will probably ignore that one and show you an application of the thing. I'm realizing that this is rather
Estás en la mitad,
en la mitad, ¿no?
sin contar la pregunta.
I will show you a couple of pictures. Unfortunately, I put them at the end. This is a very small Markov chain. This is dual. Observe that this is an irreducible thing. The dual is this chain with two absorbing states. This is a chain where there is no dual, because the monotonicity is here will not work, right? This is a general picture of a chain with three states, continuous time in the examples. This is the dual, two absorbing states. And if you observe here, this thing, this will be a Markov chain if this is less than that. We understand why, but it's strange that the math didn't work, and they work, actually, if you go to the dual, maybe you must go using our definitions. This is the dual of a birth-death process. Observe that in the dual, lambda moves to the right, to the left, sorry, push you to the left and you to the right. This is the uniformization of the MM1. The MM1 was, forget that, and lambda to the right, mu to the left. Then you divide by lambda plus mu, because that's larger than n rate in the thing, the system. So P is lambda divided by lambda plus mu. You see here, Q is mu divided by lambda plus mu. and you have a loop here with probability Q. This is the uniformization, and the uniformization process allows you to work here to solve for the continuous time one. This is the dual of the uniformization, and this was our target. If I have time, I can explain why it's better to work, much better to work here than to work here. Is the key to obtaining closed form, closed forms. So I will briefly describe the power dual thing. Here. So you have a matrix having n element, any rows and columns. The power dual has one more row, one more column, and is given by these formulas. All you have to see is that it's linear, and it will be linear in the case, which is always our case, the sparse things, is linear in the non-zero elements of the original matrix. So it's a linear transformation. Here you have an example in dimension 2. An example of whatever the dimension. Here is any matrix. Here is a stochastic matrix. Here is the dual, the power dual of that one, and also the Sigmund dual of that one, because this is stochastic. So we are in the Markov world. Here we obtain this number. So this thing is not anymore Markov chain matrix. Here is another stochastic matrix, and the dual is also a stochastic matrix. So sometimes it is, sometimes it's not. Let's ignore that one. In the properties, perhaps this resumes the property. When you compute the power dual or the Sigmund dual, you obtain what is called in the literature a somewhat stochastic matrix. The definition is all the rows have some one, but the elements need not to be probabilities. Can be numbers, negative numbers, or numbers larger than one. So it's not a stochastic matrix, but it's somewhat stochastic. There is an inversion lemma saying if you give me the dual, I can compute the original one with similar transformations. And another remark, if you take an arbitrary, somewhat stochastic matrix, and you apply these inversion formulas, you obtain another stochastic, somewhat stochastic matrix, whose dual is this, the original one, the one I received. Okay, is, again, because it's not clear, the inversion is to go back, give me the dual, I find the original one using these formulas. And this thing says, if you give me any somewhat stochastic matrix, if I apply this, I obtain a matrix whose dual is that somewhat stochastic matrix you gave me. You prove some properties, just not hard to, it's not hard to do. The dual of a product is the product of the duals in the commuting. And the power of the dual of the power is power of the dual. So that gives this scheme to compute the power of a matrix, whatever the technique you want to use. Another possibility is to go to the power dual, then apply your tool, favorite tool, to compute the power, and then invert. The exponential dual is similar, not exactly the same. Similar is more complicated. You need to prove a couple of theorems that go to the limit. But I know I will not have time to go there. Some references, the original paper for the EMM1, the case of the exponential dual, and we didn't publish still the case of discrete-time, the power dual. In a survey I wrote a few years ago about all these topics. In my application, very briefly now, I think, very briefly is the following. I will come back when I will need this notation if we can do it. Yes, I have. So I call L, which is the original. This is L, dimension 4, okay, upper triangular with ones. This is R. And this triangle is 0, 1 single diagonal, -1, the next one, and then zeros. You can prove that the dual, this is a matrix representation of duality. That means the following. You give me M, I transpose, multiply by L to the left and by R to the right, and I get almost all the dual, the northwest of the dual, which means every row and column except the last column and rows. And then I fill explicitly the last column and row. So there is a matrix expression for this transformation that helps making the computations. And now in my example, okay, I will not get very detailed. My example is take now an absorbing process, because this appears in applications on reliability. The critical failure of the system corresponds in the model to an absorption by one of the states. Here I took something having a name, the Gamble-Rubin problem, famous one in probability. You are given a Markov chain having two absorbing states, one to the left, one to the right, and you want to compute the probability starting at any state to be absorbed to the left and or to the right. And what you prove is the following. This is the northwest of this data. I define that as a tilde because I will think of this as a dual. I know that, I call P the unique matrix inversion whose power dual is this thing. There is unicity in inversion lemma. I can prove very easily that it's somewhat stochastic, not necessarily stochastic. And basically what we proved here is that you can do with this thing, which is not Markov, the same manipulations as you do with a Markov chain, writing the equilibrium equations, especially making cuts in the state space and writing equations for the equilibrium between the flows going from one of the classes to the other one, which is always true if equilibrium exists for your Markov chain. But here we are in an abstract world, and we compute a kind of stationary vector, and doing all that process, you can compute the absorption probabilities easily and can extend this to any process with absorption states. And I will stop here.